What's up? I'm Vin and I'm solving nonlinear inequalities. So first up, we have this inequality, and the first thing I want to do is treat this inequality as if it's an equation. So I'm going to set x plus 4 times x minus 2 times x plus 5 equal to 0. And from here, factors and roots have an opposite relationship. So x plus 4 would give us a root of x equals negative 4. X minus 2, this factor would give us a root of x equals positive 2. And the last factor would give us a root of x equals negative 5. And from here, what we're going to do is we're going to write these numbers on the number line. So we have negative 5, and then we have negative 4, and then we have positive 2. And from here, what we're going to do is we're going to label these points as part of our solution set. The reason being, the inequality here is a less than or equal to 0 inequality. So that means the values of x that make the left side equal to 0 are part of the solution set. But then the next thing we have to do is check these 4 intervals to see when we plug in an x value on each of these 4 intervals, which of the intervals will make the inequality true. So what I mean by that, we have the interval from negative infinity to negative 5, and then we have the interval from negative 5 to negative 4, and then we're going to look at the space from negative 4 to positive 2. And then finally, we look at the space from 2 to infinity. So on this first interval, let's say we plug in x equals negative 6, something less than negative 5. We're going to plug this into the original inequality. So we plug in x equals negative 6. That's going to give us negative 6 plus 4. And then we're going to have negative 6 minus 2. And then we're multiplying all of that by negative 6 plus 5. And from here, we could find the actual value of this. But when we're doing this, we really just have to worry about if our answer is positive or negative. So negative 6 plus 4, I just say, okay, that's negative. Negative 6 minus 2 is negative. Negative 6 plus 5 is negative. And when I multiply a negative times a negative times a negative, I get a negative number. The reason being is we have an odd amount of negatives. If we have an even amount of negatives, then the product goes to something positive. But now if we actually work this out, this is going to give us, we're going to have negative 2 times negative 8 times negative 1. And this is going to work out to negative 16, which we ask ourselves, is this less than or equal to 0? This is a true statement here. This is true, which tells us that this interval from negative infinity to negative 5 is part of our solution set. Okay, so we can include this. This is part of our solution set. So for the next interval here, let's say we plug in x equals negative 4.5. We need something between negative 4 and negative 5. So we plug this in, and let's see what we get here. So we're plugging this into the original inequality. We have negative 4.5 plus 4. And then we have in the next factor here, negative 4.5 minus 2. And then we have negative 4.5 plus 5. So this one here is going to be a little different because here, negative 4.5 plus 4 works out to negative half, but that's a negative number times another negative number. When we do negative 4.5 minus 2, we get negative 6.5, and this would work out to positive 0.5. So now I'm doing a negative times a negative times a positive. And we have to ask ourselves, is this going to work out to something less than or equal to 0? This one is not true. Okay, this product would work out to a positive number, which is automatically greater than 0. So this one here, this space is not part of our solution set. So now for the next one here, we're going to plug in a number between negative 4 and 2. So let's say we plug in x equals 0. And when we plug in 0, we're going to have 0 plus 4 is going to give us 4. 0 minus 2 gives us a negative 2. And then 0 plus 5 gives us 5. And we could actually work this out, or we could just ask ourselves, the product of a positive times a positive is going to give us a negative number, which is in fact less than or equal to 0. So I know this one here is going to be true, but if you actually want to work the product out, you can. We'd have 4 times negative 2 is negative 8, and negative 8 times 5 is going to give us negative 40. So this one here is true, which means that the numbers from negative 4 to positive 2 are also part of our solution set. And now for the last interval, from 2 to infinity, we could plug in something like x equals 3. So we plug in, we're going to have 3 plus 4 times 3 minus 2 when we plug in x equals 3 to the next factor, and then we have 3 plus 5. And notice here that we have a positive number times a positive number times a positive number. So will that product work out to something less than or equal to 0? No, this one here is not true, which means that the numbers from 2 to infinity are not part of the solution set. So now let's write down the solution. The solution here, we have the first interval. We're going from negative infinity to -5, but we are going to include -5. The reason being, the inequality in the beginning was less than or equal to 0. So at x equals -5, that would make the third factor 0, which would make the entire left side equal to 0. So that's why we are including it in our solution set. And then the next space we look at is this space over here. That's all the numbers from -4 to +2. And once again, we are putting brackets because our inequality was less than or equal to 0. So one last thing before we move on, let's type in the left side of the original inequality into the y equals. We press graph, and now let's see what our solution means. So the solution is the x values from -infinity to -5. And remember, we had an inequality where the left side was less than or equal to 0. Graphically, that means the graph is on or under the x-axis. So notice that from -infinity up to -5, the graph is under the x-axis. And then it goes back under the x-axis at -4. It hits 0 and it goes under. And it's under the x-axis until we get to x equals +2. The graph reaches 0 again, and then it goes above. So our solution checks out. Question 2, we're going to start it the exact same way. We're going to treat this as an equation. We're going to set x plus 3 squared times x minus 1 times x minus 4 equal to 0. And from here, we find the roots. This first factor is being squared, but we just have to worry about when is the inside equal to 0. So the inside we could say is equal to 0 when x plus 3 is equal to 0, and x plus 3 is equal to 0 when x equals -3. So this is our first value that we're going to look at on the number line. And then we have the next one here, x minus 1. This factor is going to give us a root of x equals 1. And then the third factor, x minus 4, will give us a root of x equals +4. So from here, we write these values on the number line. But this time, things are a little bit different. What we're going to do this time is we're going to put open circles at these values. The reason being is that our inequality is strictly greater than. Okay, so that means that the roots are not going to be a part of the solution set this time. And now, from here, we're going to do what we did before with the intervals. The first interval we're going to look at is from -infinity to -3. And then we're going to look at the interval from -3 to +1, and then we look at the interval from 1 to 4, and then finally we look at the interval from 4 to infinity. So we are going to plug in test values here, and on this first space we're going from -infinity to -3. So let's say we plug in x equals -4 into the original inequality. Now there's one thing here that we have to be very, very careful of, and you'll see in a moment. Around the factor x plus 3 squared, there's going to be something very significant about the fact that our power attached to this factor here is even. Okay, so we're going to pay attention to this detail and see what it means for when we fill out this number line here. So we plug in x equals -4. We're going to have -4 plus 3, and this is being squared, and then we have -4 minus 1, and then we have -4 minus 4. And we want to know, is this greater than 0? Well, -4 plus 3 squared is going to give us something positive. Okay, we're going to have -1 squared, which is equal to +1. This works out to something negative, and this one works out to something negative. So right away, I could see we have a positive times a negative, which is positive. So the first interval is looking good. This one is going to work out to something true, so we could say this whole interval is part of our solution set. If we actually simplify here, we're going to have -1 squared is equal to 1, and then we have times -5, and we have times -8. And this is going to work out to +40, which is greater than 0. So once again, this interval here is fine. But one thing we have to be very, very, very careful of. Students will look at this and say, oh, I bet each time things just alternate. So in the last example, we had something that worked, didn't work, worked, didn't work. So they might go check X, check X. But be careful, this is a very dangerous bear trap. We have to make sure that we test each interval. There is a shortcut that we could use here, but let's just investigate first and see what we could learn from the fact that this binomial here is being squared. So let's say I plug in x equals 0. When I plug in x equals 0, what we're going to have is we're going to have 0 plus 3 squared. And then we're going to have 0 minus 1. And we're multiplying by 0 minus 4. Over here, we're going to have, if we work this out, 0 plus 3 squared is going to give us 9. So we have 9 times negative 1 times negative 4. And this is going to work out to positive 36. Reason being, we have a negative times a negative is positive. So we get something here that also works. So why didn't it alternate? And the reason being is that our power here is even. So anytime you have an even power attached to your factor, that means that there's not going to be a change around this, okay? Graphically, what that means when you have a root that comes from a factor being squared, that's when you have something that is either going to be looking like this, or it could be something that looks like this, okay? That's when your graph is tangent to the x-axis, but it doesn't actually go through once it hits the x-axis. So that's what's happening here, and that's why we do not have a sign change around here, okay? If I say that on this interval, I had a positive output value, then this interval, I had another positive output value, there's no sign change because the factor has an even power attached. When your factor has an odd power attached like this, then we could say that there is going to be a sign change. So just, using what we know about the power of factors and what it means about the graph, I could just tell right away that this one here is not going to work and this one is going to work. But let's still investigate it just to show that it's going to confirm what we have here. So now let's plug in a number on this space. So let's say we plug in x equals 2. If we plug in x equals 2, we're going to have 2 plus 3 squared times 2 minus 1 times 2 minus 4 is greater than 0. And if we think about this, we have a binomial being squared. So if we plug in any x value except negative 3, we're always going to get something positive because we're raising this to an even power. So this one automatically, without thinking too much, is always going to give us something positive. And then we have times 2 minus 1 equals positive 1, which is positive. But then when we do 2 minus 4, we're going to get a negative. We get negative 2. So now we think about this. We have a positive times a negative is negative. That's not going to give us something greater than 0. So this statement here is not true, which is why we're not going to include this space in our solution set. So now for the last interval, let's say we plug in x equals 5. If we plug in x equals 5, we're going to have 5 plus 3 squared times 5 minus 1 times 5 minus 4. And here we have a positive number being squared, so we get something positive. 5 minus 1 is positive 4, and 5 minus 4 is positive 1. And when I multiply a positive times a positive times a positive, I get a number that is greater than 0. So this statement here is true, which means we can include this in our solution set. So now let's write out our solution. So let's think about which intervals made the inequality true. So the first one we can include is the interval negative infinity to negative 3. And this is an open interval on both sides. The reason being this inequality was strictly greater than 0. So that means we are not including negative 3 as part of our solution set. And now we're going to also join this with the space from negative 3 to positive 1. And then the last interval that we're going to include is the interval from 4 to infinity. So just know for these questions, be very, very, very careful when one of the binomials has an even power, because around that root that comes from that binomial, you're not going to get a sign change. You're either going to have both parts included or both parts not included. So now real quick, before we move on, let's graph the left side of the inequality. And we had our left side greater than 0. So notice that from negative infinity to negative 3, the graph is strictly above the x-axis. At negative 3, the graph reaches the x-axis, and then from negative 3 to positive 1, the graph is above the x-axis. It goes under from 1 to 4, and then from 4 to infinity, the graph goes back above the x-axis. Question 3, we have this nonlinear inequality, and we're going to start by treating this as an equation. So we have x plus 2 over x plus 3, and we're going to set this equal to x minus 1 over x minus 2. So the first thing we could do is just subtract this fraction to the other side. So we're going to have x plus 2 over x plus 3 minus, and then we have x minus 1 over x minus 2. And this is all equal to 0. So now we have this rational equation. So this is a little bit trickier to solve, But what we want to do is we want to look for a least common denominator. So the least common denominator, we're just going to focus on the denominator of x plus 3 and the denominator of x minus 2. So the least common denominator here would be x plus 3 times x minus 2. So now we could take this equation and we want to make matching denominators. So we have x plus 2 over x plus 3. That first fraction we're going to multiply by x minus 2 over x minus 2. And then we have minus x minus 1 over x minus 2. That second fraction we're going to multiply by x plus 3 over x plus 3. And now we could see here that our fractions have common denominators. So now this we could just work out. I'm going to leave the denominators in factored form, and I'm going to actually multiply out the numerators. So for the first fraction here, we're going to have x plus 2 times x minus 2. Just think of the difference of two squares formula. A plus b times a minus b gives you a squared minus b squared. So I'm just going to use that idea over here and just say x squared minus 4. And I'm going to leave the bottom in factored form. You'll see why later on. So we have this, I'm leaving in factored form, and then minus, I multiply these two, and now I would have x times x is x squared. I would have x times 3 is plus 3x, and I have negative 1 times x is negative x. So when I do 3x minus 1x, I'm going to get a plus 2x in the middle. And then I have negative 1 times positive 3 is negative 3. Okay, so I could show how to multiply it all out, but this question we have way bigger stuff to worry about. So we're just multiplying these two binomials. You're using FOIL, or you're just using the distributive property. So now on bottom, we have the x plus 3 times x minus 2. I could move the order around because multiplication is commutative. So I could say x minus 2 times x plus 3, or vice versa. And now this is all equal to 0. So now for the next line, we have to be very careful. We are going to combine these into a single fraction because we're subtracting and we have matching denominators, but we just have to be very careful and make sure that we distribute the minus sign. So we have x squared minus 4 first, and then we're going to distribute like this. So think of this as negative 1 times x squared is negative x squared, negative 1 times 2x is minus 2x, and negative 1 times negative 3 is positive 3. And all of this is equal to 0. So from here, we can combine like terms. X squared minus x squared cancels, and then we have just a negative 2x on its own. And then negative 4 plus 3 makes negative 1, and this is over x plus 3 times x minus 2, and we're setting this all equal to 0. So from this step here, we want to find when is the left side equal to 0, and just know that a fraction is equal to 0 when the numerator is equal to 0 and the denominator is non-zero. So from here, we could set negative 2x minus 1 equal to 0. So we have minus 2x minus 1 equals 0, and this is going to give us negative 2x equals positive 1 after we add 1 to both sides, and now we just divide both sides by negative 2, and this tells us that x equals negative 1/2. But we should also look at other values of x. We should also look for where is the left side undefined. Okay, so we're going to also set the denominator equal to 0. So we're going to have x plus 3 equals 0, but this is something that we don't want to happen, okay? Because if x is equal to negative 3, you could even see the original expression here, or the original inequality, becomes undefined. We can't have division by 0. So I'm going to say right away, x plus 3 is not allowed to equal 0, which tells us that when we make our number line, x cannot equal negative 3. And by that same line of thinking, we also have to say that x minus 2, this also cannot be equal to 0, because if x minus 2 is equal to 0, we would have division by 0 on the right side of the inequality. So this tells us that we can't have x equal to positive 2. Okay, so these are the significant x values that we have to include when we are building our number line. So now let's build a number line here to find our solution set. So I'm going to include negative 3 on our number line, and I'm going to put an open circle here, and I'm going to write a little u above this, because if we were to plug in x equals negative 3 to the original inequality, it would make our inequality undefined. And then we have x equals negative 1/2. This we're going to include, and x equals 2. But once again, I'm going to put an open circle here and put a u to mention that if I plug in x equals 2, it makes the inequality undefined. At x equals negative 1/2, I'm going to put an open circle as well. The reason being, this inequality is strictly less than. Now, one thing before we plug in our test values, just know that you do have to include the values of x that make the inequality undefined, because even though they're not necessarily in the domain, if we were to treat this as a function, like let's say I were to treat this as f of x equals x plus 2 over x plus 3, and then minus x minus 1 over x minus 2. Let's say I were to treat this as a function. Even though these x values are not in the domain of the function, we could still have a sign change in the function from positive to negative or from negative to positive. Okay, so the y values can change signs at the asymptotes. You could have a situation where, let's say you have an asymptote at 2 and you have something that maybe goes up here and goes under like this. So the y values go from positive to negative, even though the graph does not pass through 0. Okay, so this is just something here that we have to mention here in our number line, because if we leave those values out, which is a very common mistake, it can make our solution set incomplete. So that's just something, once again, we have to include. So now let's investigate. I'm going to plug in something on the space from negative infinity to negative 3. So let's say we plug in x equals negative 4. So if we plug in x equals negative 4 to the original inequality, we're going to have negative 4 plus 2 divided by negative 4 plus 3 is less than, and then we have negative 4 minus 1 over negative 4 minus 2. So now we simplify this. This is going to give us, we're going to have negative 2 over negative 1 is less than, and then we have negative 5 divided by negative 6. So here we have a negative over a negative goes positive. So we have 2 is less than, and we have a negative over a negative going positive, 5 over 6. But this is not true. Okay, this statement here is not true, which tells us that this space here is not part of our solution set. So now we have to plug in a number on the space from negative 3 to negative half. So let's say we plug in x equals negative 1. So if we plug in x equals negative 1, we'll have negative 1 plus 2 over, and then we have negative 1 plus 3 is less than, and we have negative 1 minus 1 over negative 1 and then minus 2. So if we work this out, we have negative 1 plus 2 is 1 over negative 1 plus 3 is 2 is less than, and here this gives us negative 2 over negative 3, and this simplifies to 1/2 is less than 2/3, which is true. This statement here is true, which means that this space is part of our solution set. So next we'll plug in something between negative half and 2, and let's say we plug in x equals 0. So if we plug in x equals 0, we're going to get 0 plus 2 is 2 over 0 plus 3 is equal to 3 is less than 0 minus 1 is negative 1 over 0 minus 2 is negative 2. And if we simplify this, this gives us 2/3 is less than negative 1 over negative 2 goes positive, and we get 1/2. And 2/3 is not less than 1/2. This one here is not true. So since this one is not true, this tells us that this space from negative half to 2 is not part of our solution set. So now the last space to check is the space from 2 to positive infinity. And here, let's say we plug in x equals 3. So if we look back at the original inequality, we're going to have here, we'll have 3 plus 2. I'll write it over here, and then I'll just drag it down. 3 plus 2 over, and then we have 3 plus 3. And then is this less than, we have 3 minus 1 over 3 minus 2. So this one, we could work it out. We have 3 plus 2 is 5 over 3 plus 3 is 6 is less than 3 minus 1 is 2 over 3 minus 2 is 1. And this is a true statement. 5 over 6 is definitely less than 2 over 1, which simplifies to 2. This one here is true, which means this space is part of the solution set. So our solution here, we could just say, is going to be built by two intervals. We have the interval from negative 3 to negative half, and then we're going to write union, and the next interval is the interval from 2 to infinity. So this is our solution. So this one is a little bit trickier to check. So what I'm going to do is I'm going to subtract that fraction to the other side. So I'm going to type this in the calculator as we have x plus 2 over x plus 3. And then we're going to hit the right arrow to get out of this, minus, and then I'm subtracting x minus 1 over x minus 2. So I'm going to press alpha y equals enter to pull up a blank fraction. We have x minus 1 over x minus 2. And we will compare the graph to our solution set. So we press graph here, and remember, we subtracted the fraction on the right to the left side. So we have the difference of those two should be less than 0. So we're looking for which part of the graph is less than 0. So notice that we have a vertical asymptote at x equals -3. Okay, that was the significance of the values where the inequality was undefined. It makes vertical asymptotes on the graph when we check. So from -3 to -half, notice the graph is under the x-axis. And then we notice here from 2 to infinity, we have the graph is under the x-axis. That's because we have a vertical asymptote at x equals 2. So the graph goes from above to under without passing through the x-axis. But this part of the graph stays under the x-axis, once again, from 2 to infinity. So our solution checks out. Question 4, we have this nonlinear inequality. And this question I want to do a little bit differently. So I'm going to say f of x equals the left side, natural log x, and then plus 1. And the reason I'm doing this is the domain of f of x plays a big part of the solution set of this inequality. So for f of x, we have this natural log x piece. And when you have a natural log x, the x values have to be positive. You can't have natural log of -5 or something like that. So the domain is very, very, very important for a question like this, because we have to only consider solutions that are part of the domain of the functions involved. So now we could set natural log x plus 1 equal to 0. We will treat this as an equation. And we go -1 on both sides. And this gives us natural log x equals -1. And to solve for x, we have to know that natural log and e are opposites. So we could exponentiate both sides. We make both sides powers of e. E and natural log cancel out. So x equals e to the -1st, which we could say x is equal to 1 over e. So now we can make our number line to look for the solution set. But remember, the number line has to start at 0. 0 is not part of the solution because natural log of 0 is undefined. So just imagine here we have an open circle at the beginning, and the only value to consider on the number line where a sign change or the inequality could go from being true to not true can occur is going to be at 1 over e. Okay, so at 1 over e is where the change could happen. So this is maybe a little bit tricky. We have to think of a number between 0 and 1 over e. And let's say we're doing this without a calculator. Well, if we want to make this number smaller, one thing we could do is we could multiply it by 1/2. So just imagine we have 1 over e, and we multiply it by 1/2. We could say this is equal to 1 over 2e. So now when we look for solutions to the inequality on the space from 0 to 1 over e, we could plug in x equals 1 over 2e. Okay, so we have 1 over 2e. This is what we're plugging in. So now we have natural log of 1 over 2e like this, and then plus 1. We want to know, is this greater than 0? So without a calculator, this is a bit of an interesting question. If I'm doing this without a calculator, what I'm going to write is I'm going to say natural log of 1/2 times e to the -1st, and then plus 1 greater than 0. So we want to see if this is true. And then we could use properties of logs. We have a product inside, so we could write this as natural log of 1/2, and then plus natural log of e to the -1st. So I'm just breaking this up into two separate logs like this, and then plus 1 greater than 0. So from here, we have natural log of 1/2, and then natural log and e are opposites, so they cancel out. So we have natural log of 1/2, and then we have -1 plus 1 greater than 0. And then -1 plus 1 cancel. So now the question is, can we say natural log of 1/2 is greater than 0? So this is where it really helps if you know the basic structure of natural log x, the function. So if I were to just sketch natural log x, the function looks like this. It is the opposite of e to the x, which looks like this. They have symmetry over y equals x. And natural log of x is equal to 0 at x equals 1. So if I'm looking at natural log of 1/2, I'm going to get a y value here that is less than 0. So this one here is not true. Okay, this statement here is not true. So this space is not going to be a part of our solution set. So now let's say I plug in something greater than 1 over e. We should know that e is roughly 2.718, and this number is irrational. The decimal just goes on forever. Okay, but knowing that e is roughly 2.718 tells us that 1 over 2.718 is less than 1. So I could plug in x equals 1, and I can confidently say that 1 is greater than 1 over e. So when I plug this in, now I have natural log of 1 plus 1 is greater than 0, which gives us natural log of 1 is 0, 0 plus 1 is greater than 0, and this statement here is true. So that means that this space here is part of the solution set. But look at the beginning of the question here. We have an inequality here. We're looking at natural log of x plus 1 is strictly greater than 0. So that means that this root that we found from this equation is not going to be a part of the solution set. So now we could write out the solution. The only interval that satisfies the inequality is the interval from 1 over e to positive infinity.